let's look at the cases with voltage sources. If we have voltage source, they will fall into one of three scenarios. The first one is the voltage source is in series with some impedance, and in that case, we can apply the source transformation to turn that into a current source in parallel with that impedance. In that case, we end up with only current sources. That's kind of the base case we fall back to, right? The second case is if a voltage source is not in the in series with the impedance, we choose the one end of the voltage source as the reference node. So in that case, we will show you in the example how we're gonna deal with that. And the third case is no matter what you do, there is a voltage source that's kind of floating. That means neither end of the voltage source terminals is connected to the reference node. So in that case, we use the method called the supernode. And in the old text, old reference books, you could move around this voltage source instead of doing the supernode. But in this case, I'm following the text, the convention. So we're gonna look at three examples. In this case, I'm not gonna work all into the very end. So I'm gonna write the equations. Then I'm gonna stop there. Otherwise, the video will probably take too long, for unnecessarily too long, right? So the first one here, let's see if we have the case. So this is case number one. We have a voltage source. Why the reason the voltage source is an issue in the node voltage analysis? Remember the node voltage analysis, we're writing the KCL equations, right? We want the current source as the known variable, known quantities, so that we can solve these equations of node voltage and with node voltage unknowns. But if you have the voltage source, you don't really know what's the current through those voltage sources. That's actually the main issue is. So in this case, the 12 volt. By the way, you recognize this voltage source for those who didn't recognize, right? So this is a voltage source, and this voltage source is in series with this impedance. In this case, the impedance is just a 4 ohm resistance. So what we can do is we can turn this thing here, we can transform to the resistance. This is still 4 ohm. Then in parallel with a current source. The current source here is 12 over S divided by 4. That's equals 3 over S. Okay, so we're gonna replace this. Maybe I should redraw this circuit. Let's see, I have 2 over S. I have a 2, 3, 5 over S. So this is the V1. This is V2. And this is V3. So in this case, we are still having it here as a reference node. So in this case, we can, since we only have a current source now, and then we can use the kind of write the matrix form by inspection, right? So let's try that. And in this case, let's see the matrix is going to be 3 by 3, right? And for the first one and the diagonal elements, that's the sum of the admittances. In this case, we have 5 over S plus 1 over 3. And between 1 and 2, I got a negative 1 over 3. And between 1 and 3, I got a 0. Between 1 and 3, I got a 0. And for the for the node number 2, and I have between 1 and 2, I get negative 1 over 3. By the way, the matrix is symmetric, right? And for at node 2, I got a 1 over 3 plus 1 over 2 plus 1 over 3s. This is 3s, right? Yes. So that's 1 over 3s. And between 2 and 3, that's negative 1 over 3s. And then the matrix is symmetric, negative 1 over 3s. And at node number 3, I have 1 over 3s plus 1 over 4. And then multiplied by the V1, V2, and V3. That's equal to the current sources entering that each node, right? So at the node number 1, we have then node number 1 we have 2 over s, and node number 2 I got a 0, and node number 3 I got a negative 2 over s plus 3 over s. If you get this should be negative 6 over s. I should leave this, so you know where this is coming from. Okay, so this is going to be the node voltage equation for the first case. And for a second case, let's see if you have node voltage equations. In this case, we can still, in this case, I have the voltage source here, right? Again, you recognize the voltage source. This is a current source. For those who didn't know, I hope now you know. So the voltage source is now the one end of the voltage source is connected to the reference node, right? So the rest thing here is we can still write the node voltage equation and node number 1 just as we did before. And in this case, it's hard to directly write the matrix form by inspection because we have this voltage source here. Okay, so we're just gonna follow the basic steps. We just write the node voltage, the KCL equations at each node. So let's start with the node number 1, and that's still the V1 S over 5 over S plus V1 minus V2 divided by 3. This is the current leaving from the capacitor impedance and the resistance. That's equal 2 over S. It's the first equation, and then node number 3 and node number 2 we just as we did before, so V2S minus V1S divided by 3 plus V2S over 2 plus V2 over minus V3S over 3S equal 0 because there are no current. And node number 3, we can't really write any KCL equation because the current through this voltage source is unknown, right? So luckily, and since this already, we can write the node equation based on the element constraint directly. So this V3 is just equal the voltage the source voltage here because the orientation of the voltage. So these are 3 equations we can write for this case. And let's see the last case. The last case here is we have 2 voltage sources here. Recognize this another voltage source, right? This is one voltage source we had before. And in this case, I just chose this point. You can choose this point, or you can choose this point, or you can choose this point. No matter what you do, one of these voltage sources is going to be kind of floating, not connected to the reference node. So what we do is we use this as a super node. You just write the KCL for this one. You do not create another variable. And in the past, some students create another variable for the supernode. We have enough unknowns. We don't want additional unknown for this supernode, right? So we're still using V1 and V2. When we write the KCL as unknown, we will write the KCL equation. So let's see, as a supernode, so we still have 3 unknowns. Hopefully we can get 3 equations. Supernode, and the KCL equation we have is V1, the leaving current through 5 over S, plus through that 2 ohm resistance as V2 divided by 2, right? That's current, and also through that 3S impedance, and that's V2 minus V3 divided by 3S. The current entering that node is 2 over S. That current source there, right? And we cannot write any other KCL equation anymore, right? So the voltage, the node voltage V1 and V2, they are related to each other by we can write another equation inside this supernode. So in this case, we have V1s minus V2s, that's equal negative 5 over s. Or you can do, you can write V2 minus V1 equal 5s, and that's fine too. Okay, there is no kind of certain convention we have to follow, because now we cannot rewrite anything by inspection anymore. So in this case, we have for the node number 3, we have V3 s equal to 12 over s. So these are 3 equations we get. Right. So that's for the other cases we deal with for the node voltage analysis, except for that have independent sources. We're going to deal with that in the last video clip. Okay, I'll see you in a moment for the mesh current analysis.